Alright, so this video is to go over intermolecular forces. So there are a few things that we need to go over before we talk about intermolecular forces. One of them is go back to electronegativity. So we introduced this topic while you guys were looking at periodic table trends, and I said I was going to revisit, and here it is. So electronegativity is the ability of an atom to pull electrons towards itself. This is the trend. So electronegativity increases as you move up the periodic table, and electronegativity increases as you move across the periodic table. This trend you will need to know, so make sure that you have that written somewhere. Okay, so if I look, for example, at nitrogen versus oxygen, I would say the oxygen is more electronegative than nitrogen. And again, because it's moving this way. This little table over here actually gives you numbers. So the numbers that you see, 2.1, 1, 0.9, 0.8, are actually electronegativity numbers. So electronegativity can be measured. Okay, and you can see here fluorine, which is the most electronegative element in the periodic table, has electronegativity of 4. 4 is the maximum in this scale. Okay, so the scale goes all the way up to 4. Right, so then we need to introduce another concept, which is polarity. Polarity is the separation of charge in a molecule in a compound. Okay, so we say that a compound or a molecule, actually a molecule in this case, is polar when the bonding electrons are not shared evenly. So remember that we mentioned that covalent bonding is the sharing of electrons. Well, the electrons, just because they're being shared, doesn't mean they're being shared evenly, right? And then we call nonpolar, those are bonding electrons that are shared evenly. In order for us to determine what's polar and what's nonpolar, two things comes to mind. One is shape, so the shape of a molecule. And that was the part 3 of your last lesson. Okay, that was a video that I created on shape of molecules. So if you need to revisit that video, I recommend that you either go back to the lesson or send me a message asking for the link. And then electronegativity is the second part. Alright, so if we look at electronegativity, okay, here again is the scale from 0 to 4, 4 being the most electronegative. This one in this case is electronegativity difference. And we look here at the different types of bonds. Ionic bonding obviously has the greatest electronegativity because you're bonding something very weak, very low electronegative, to something very high with very high electronegativity that is actually a separation of charge. So obviously it's very polar. Then on the list, farther down is the polar covalent, electrons shared unequally. And it has a partial charge. This symbol over here is a lambda, and it represents partial. So it doesn't have a full charge like here, it has a partial charge. Okay, so it's partially negative, partially positive. Okay, and a pure nonpolar covalent bond, which electrons are shared equally, there's no partial charges. Okay, so I'm going to showcase this by showing you this simulation. Alright, so we have two molecules here, A and B. Okay, and I'm going to put partial charges. Okay, I'm just going to make them even now. Second. Alright, so this represents the direction that the electrons are moving, and here represents partial charges. It has no partial charges because the electronegativity on those two bonded elements are equal. Okay, electronegativity for B, electronegativity for A. The other thing that I'm going to show here, just to showcase charge, is that I'm going to put an electric field. Okay, so this is an electric field where one side is positive, the other side is negative. And if I move the molecule around it, there's no repulsion, there's no attraction, because again, the molecule is nonpolar. Okay, it has no charge. Great. So now let's change this up. So now I'm going to make, it doesn't matter, I'm going to make A different, either less than electronegative or more electronegative. So let's make it less. So if I make A less than electronegative, let's predict here what's going to happen. If A is weaker, the electrons of A are going to try to shift towards B. And that's exactly what's going to happen. Okay. All of a sudden now, A has a partial positive, meaning that it's feeling less the presence of electrons. B is becoming partial negative because it's feeling the presence of the electrons that belong to A. Okay. I can go the other way, and I can make A more electronegative, so A is going to pull those electrons. Okay. So notice that now it flips. So now A is feeling the presence of electrons, and B is supposed to be the weaker, right? It's feeling less electrons. The other thing that you should have noticed that happened is that it flipped. That's because the molecule is under an electric field. Okay, so it is going to align itself so the opposite charges are as close as possible to each other. Okay, so opposite charges. So I can move it around, and nope, it's going to go positive to negative, positive to negative. Okay, that's how electric fields work. And by the way, that's going to be important for intermolecular forces because that's how they're going to align themselves. Again, I can try, and again, if I make both strongly electronegative, again, I'm going to make them nonpolar because they have equal distribution of charges. All right, so then let's take under consideration shape. Okay, I'm going to make them all the same for now. Okay, so I made them all the same electronegativity. Okay, I'm going to put partial charges. That should be none because they have the same electronegativity. I'm also going to bring back the electric field. Again, I can move them around. Nothing happens to them. Okay, so now let's look at two cases. Let's look at a case that there's a difference in electronegativity in B. Okay, it doesn't matter if it's A, I guess it does. Let's just make A less, or B less electronegative. So if B is weaker, its electrons from B are going to move to, some's going to move to C, some's going to move to A. Those are going to be partially negative, meaning that they're feeling the presence of electrons more. B is going to be weaker, it's going to feeling the presence of the electrons less. That's what the plus and the minus represent. Notice how they align themselves. Again, partial charges, positive to negative, positive to negative. Okay, and I can try to move them around and that won't happen. Now let's go the opposite way. Let's make B the stronger one. Okay, so now B is the stronger one. B is electronegative, is the most electronegative, is partially negative. Those guys are partially positive. Okay, and again, I can move it around and it's not going to make any difference. And another example that I can do is I can make either A or C with higher electronegativity. Again, if I make higher electronegativity, it's going to have a slightly negative charge. This region is going to be partially positive, this region. Okay, so I want to show you one more thing, and it's here. Okay, so this molecule right now there's a partial positive here and there's a partial negative here. Okay, however, if I change the shape of the molecule, all of a sudden they become nonpolar. And let me explain the reason for that. It's because the dipoles, here we go. So notice how the pull of the electrons is this way, represented by this arrow. The pull of the electrons this way, represented by this arrow, they cancel each other out. So even though there's a polar bond here and a polar bond here, the overall molecule is nonpolar because it is symmetrical. So remember, I said two things. important for the molecule polarity. One is electronegativity, the other one is symmetry. When we look to see if something is symmetrical or not, you have to do this. You have to look at the molecule from this way, from the x-axis, and ask, are they the same? And then cross them again from the y-axis and ask if they're the same. And I'll show you an example of that. Alright, so let's look at some real cases. This is hydrogen bonded with fluorine. Okay. Hydrogen is very weak in terms of electronegativity. Fluorine is very strong, so it's going to pull electrons towards fluorine, so the molecule is going to be very polar. It's going to be there will be a positive pole and a negative pole. Let's look at a very important example. And by the way, I left this came from your textbook. You're welcome to pause the video and read all of this, but I'm going to explain quickly. So this is the shape of water. Okay, it's very tempting to just take water and make it straight. Okay, but that's not the shape of the water. This is the shape of the water. Okay, it is a bent shape, by the way. Again, back to the previous lesson where we look at shapes. So oxygen is very strong, hydrogen is weak. So the electrons are going to be pulled towards oxygen, leaving the hydrogen partially positive. So water molecule will have a partial positive pole and will have a partial negative pole. Okay, let's look at carbon dioxide. So here's carbon dioxide. You have carbon, which is weaker than oxygen. However, just like the example I gave before, the oxygen is pulling this way, the other oxygen is pulling this way. The vectors cancel out, so overall, the molecule is nonpolar. Okay, so the overall molecule is nonpolar because there's not one single pole, right? Or there's not a positive pole and a negative pole, right? They're pulling in opposite directions. Okay, so now we can talk about intermolecular bonds. So there's a difference between intramolecular versus intermolecular. So I'll just read it here and then I'll explain. Intermolecular forces are the forces that holds atoms together within a molecule. Intermolecular forces are forces that exist between molecules. So far you have been studying intermolecular forces. Those are bonding. Those are metallic bondings, ionic bonds, covalent bonds. Okay. Intermolecular forces is what I'm going to introduce now, which is the force between molecules. So some molecules stick together. Okay, and you can see in your daily life, if you notice, if you pay attention to water stick together, right? So here's a representation of it. So here you have the intramolecular forces, which is represented by this dash over here. Okay, it's a bonding. And then you have intermolecular forces, which is just molecules really just sticking together. So again, this is a force between atoms. This is a force between molecules. Very, very important for you to distinguish that. Okay. So, like I said, water tends to stick together, and when a set of molecules, those models of molecules, so when molecules, they're polar, okay, and this happens when they're polar. When molecules are polar, they tend to stick together just like the electric field, where they align themselves, where the positive attached, kind of is attracted to the negative, the positive is attracted to the negative, just like the electric field. So they're going to stick together. And I have this video just showcasing that. Again, it's not bonded, right? Those intermolecular forces, they can break and they can form, they can break and form easily. So they're much weaker than intramolecular forces. They form and they break very easily. Okay, I'll show you again. So there's breaking, right, and then they leave, they break in, they leave, and not a big deal. Okay, so that is the difference. Intermolecular forces are much weaker. So it even says over here, weaker than intramolecular forces, which is ionic, covalent, and metallic bonding. Okay. Another important point for you to remember. So how does this reflect, again, this whole unit we're talking about, okay, so how does this affect properties of substances? How does this affect properties of substances? Well, intermolecular forces affect a lot of properties. I'll mention few of them. A couple of them you're going to be studying in your lab. So the first thing is melting point and boiling point, right? The one thing before we talk about this is that you need to remember that a melting point is a transition between a solid to a liquid, or a liquid to a solid, depending on the direction that you're thinking about this. But usually when we think about melting point, we're talking about a solid going into a liquid. Okay, it's the temperature at which this happens. Okay, notice that as a solid, it's very structured and very close together, except for water. As a liquid, is a little bit more spread apart in general. Okay, and then the boiling point is between a liquid and a gas. Okay, and again, it's that temperature at which this goes from a liquid into a gas. You have to also know that solids have a very high intermolecular force, liquids medium, gas, the assumption is they have very little to none intermolecular forces because they're too far away from each other to stick together. Okay, so that's the idea. So keeping that in mind, I'm going to show you a simulation of a boiling point, so going from a liquid to a gas. Okay, so let's begin with polar. Let's begin with polar. Okay, so this is a liquid. You can see the little dashed lines of representing intermolecular forces, whereas the solid lines represent bonds or intramolecular forces. Right, slow motion, I can start here. So you can see I have some heat applied to it and they're kind of moving around. They're still in the liquid form. And you can see here the intermolecular forces keeping them from leaving and becoming a gas. And let me increase the temperature. Okay. And you can see what's keeping them from becoming a gas is the intermolecular forces. Okay, some of them are thinking about becoming a gas. Okay, and finally, water is becoming vapor. I assume this is not water actually. Whatever this polar molecule is becoming vapor. Okay. And even as a gas, you still see a little bit of intermolecular forces, but way more. There we go. So about 375 Kelvin, okay, to get this polar substance to become a gas. All right, so then let's reset. And you can see the intermolecular forces decrease drastically, right? Now let's look at a nonpolar. You do see a little bit of intermolecular forces because all substances do feel a little bit, but much, much less. So you can see, even without applying much heat to it, you can see that some of them are escaping. And we call this volatile. So if you ever look at a liquid and it says this liquid is volatile, it means that it becomes a vapor very quickly. So then let's add temperature to this. Increase the temperature, better said. And you can see as I increase the temperature, okay, it's quickly becoming a vapor and is already full on vapor at 200. So remember, for the polar molecule was 375, for this one's about 200. Okay, so that's the point I wanted to make, is that the melting point, the boiling point for polar substances are much higher than for nonpolar. Because again, they have this extra force that's keeping them together. The other property that's really important is surface tension. So when a substance is together, there's the intermolecular forces pulling them in all directions. However, the molecules that are all the way at the surface, okay, they have an even strong intermolecular forces because everything is just the vectors that's pulling them to the sides is greater. So what that means is at the surface of any liquid, there's almost a membrane-like appearance or property to it. Okay, so at the surface of a liquid, the intermolecular forces are much greater. That's what I wanted to say. So at the surface of any liquid, the intermolecular forces are much greater. Okay, and this might not be relevant to you, but it is, but it is certainly relevant to others. Let me show you here. That's not what I want to go. It was here somewhere. Oh, here we go. Okay, so let's look at the effect of intermolecular forces of surface tension. And you're going to be doing this in your lab, so I'll just move on to the last one, which is adhesion and cohesion. So adhesion is when one substance sticks to something else. Cohesion is when a substance sticks to itself. So again, I'll repeat. Adhesion, a substance sticks to something else. Cohesion, a substance sticks to itself. Again, intermolecular forces is what causes them to stick either together or to something else. Here's an example of water in a plant, right? So the water travels all the way down to the tip of the plant. That is adhesion. The water is adhering to the plant. Okay, by the way, that's how plants are able to move water from the roots to the top. But then the water creates this huge drop over here. It doesn't just come out, it sticks together. That is cohesion. Okay, so those are the two points that I wanted to make. So I think now you're ready for your lab. If you have any questions, please let me know.